All right, so we're going to look a little bit at derivatives as rates of change. So one thing we can look at is particle motion. So we have something called the position function, right? It's going to give the position of an object relative to the origin as a function of time. So as time goes on, how is the particle moving, right? Then we have something called the velocity function. So this is the change in the position function over time. So velocity is the derivative of position. Right, remember we have this instantaneous velocity. So this is how fast something is going at an exact instant and in what direction, right? So if we're talking about motion here, I've got when the velocity is greater than 0. So if we're talking about moving in a horizontal line, that means, oops, I thought I was writing. That means we're moving to the right. And if that velocity is negative, we're actually moving to the left. But if the velocity is 0, then we are stopped. And if we're moving along a vertical line, if we're positive, I'm going to just put moves up. If we're negative, moves down. And again, if our velocity is 0, then we are stopped. Right? Now, speed. So the speed doesn't tell us the direction, right? The positive and negative tells us the direction. Speed is the absolute value of velocity. So if we had a velocity, say that was -2, then we'd say our speed is 2, we'll just say miles per hour. The negative just tells us we're going left. Okay? Now acceleration, that's the rate of change of the velocity. So are we speeding up or are we slowing down? Or maybe we're not moving. So acceleration is the derivative of velocity, which means it would be the second derivative of the position function. Okay? And in this case, just because the acceleration is 0 doesn't mean that the object is stopped, like in that velocity part. It just means we're not speeding up or not slowing down. So if we're moving across a horizontal line, if the second derivative of the position, so acceleration, is positive, we could say we're pushed to the right. If it's negative, we would say pushed to the left. If we're talking a vertical line, this would be pushed up and pushed down. Now, if it's 0, the acceleration is 0, all that means is the velocity does not change. And I'll put that here too. Velocity does not change. Okay, if the velocity and acceleration have the same sign, then we are speeding up. If the velocity and acceleration have opposite signs, we are slowing down. So if we have velocity and acceleration, so velocity is positive, acceleration is positive, then we're speeding up. If it's negative and negative, I was almost going to say speeding down, but that would be called slowing down. But if they have opposite signs, so one's negative, one's positive, oh my gosh, no, that's incorrect. The same sign, they're still speeding up. It's opposite signs that they're slowing down. And I literally just said that too, which is crazy. Okay. So, okie dokie, we have a graph here. And notice this is v of t. So this is the graph of the velocity. So we're going to keep that in mind as we are looking at these questions here. So, all right, we're going to assume positive direction is to the right and that we are in feet per second. So when is the particle moving at a constant speed? So constant speed is going to be when we're at a constant on this velocity here. So when t, we can just do interval notation. We can say from 0 to 1. When is the particle moving to the right? So moving to the right, it means that the velocity is positive. So that's going to be from 0 to 2. Was it moving to the left? That's when the velocity is negative. So that's going to be from 2 to 5. When is the particle speeding up? Remember, this is when V and A are either both positive or both negative. So let me think. That's if I'm talking slopes. So slope is 0. Slope is negative. Slope is negative, and the slope is positive. So I want where the velocity is negative and where the acceleration is negative, which is going to be here. So when we are speeding up, it's going to be from 2 to 3. Right, slowing down, that's when those signs are opposite. So that is going to be from 1 to 2 and from 3 to 5. Right, when is the velocity increasing? So we're constant, decreasing, decreasing. Then we turn to increasing. So the velocity is increasing from 3 to 5. When is the velocity decreasing? It's going to be from 1 to 3. I guess we could really break it up and say from 1 to 2 and from 2 to 3. Are 6 and 7, so 3, 5, 1, 2, 2, 3, the same as 4 and 5 respectively? 2, 3, and 1, 2, 3, 5. No, they're not the same. So velocity increases where acceleration is positive. So if we're talking, all right, speeding up and velocity increasing, they would have to have the same sign. And then we can say the same thing for slowing down. They're not the same because the signs have to match up. All right, how fast is the particle moving at time t equals 4 and in what direction? So time t equals 4, I can go to the graph here. So we want the y value, so -5. So the velocity is -5. We're in feet per second. So how fast? We are going 5 feet per second and directionally to the left. What is the particle's velocity at t equals 4? Well, I just did that in number 9. It's -5 feet per second. All right, what is the average velocity over 2 to 3? All right, so the average velocity, right, it's our distance over time. So we can go look at, well, our time was from 2 to 3. So 3 minus 2. We can go find those actual function values. Erase some of my drawings here. So at 3, we're at -10, and at 2, we're at 0. But we want the average. So there's 2 points, right? 2 and 3. So we're going to take half of that. So I got 1/2 times 10, which is 5. And oh, that's a -10. And then 3 minus 2 is 1. So we'd have a -5 feet per second as an average velocity. When does the particle change direction? So that's when we're changing from either positive to negative or negative to positive, and that happens at t equals 2. How far does the particle move during the first second, and which way? So how far does it move in the first second? It's actually going to be the area of that piece of the function. And the area of that is, let's see, 1 by 5. So that's going to be 5, and it's positive. So 5 feet. Since it's positive, we'll say to the right. How far does the particle go, and when does it arrive there? So let's find all those little areas. So I did say how far to the right. So I already know that first part is 5. Let's find this area. It's a triangle, so it's 1/2 base times height. So 1 and 5. So it's 5 plus half of 5, which is 2.5. So it's going to give me 7.5. So 7.5 feet. And when does it arrive there? At t equals 2, because that's when it switches direction, right? What is the total distance traveled by the particle? So we're going to add up all of those pieces. So I already know part of it is 7.5. Let's add in the rest. I'm going to split that into 2 triangles and say, all right, 1/2 base times height. And then, so I don't need negative. And then we've got 1/2 base times height. So 15, adding in 15. So the total distance traveled is 22.5 feet. What is the particle's position after 5 seconds? So we went 7.5 feet to the right, and then that 15, we went back to the left, so minus 15 feet to the left. So that is going to give us negative 7.5 feet. And to the left, right? What is the average velocity of the particle over the 5 seconds? All right, so that average velocity is going to be that distance over time. So we just found the total distance was that negative 7.5, right? And then the time was the 5 seconds. So we get negative 1.5 feet per second. Your answers to 15 and 16 the same. So we got 22.5 and negative 7.5. No. 15 just asks for the total distance, whereas 16 is asking for its final position. It's taking in account the direction it's going, and that's called displacement. Right, what is the average speed over this 5-second interval? So the entire 5-second interval, if we're looking at, again, a total distance over time, we traveled a distance of 22.5 feet in 5 seconds. So that's 4.5 feet per second. What is the particle's acceleration over the first second? And what does your answer mean? So remember, that first part is where it was constant. So actually, the acceleration is 0. That just means the velocity doesn't change. Over what time intervals does the particle have a positive acceleration? Remember, this is where we have a positive slope, which was from 3 to 5. And having a negative acceleration is where that velocity is decreasing, or where we have a negative slope. So that's from 1 to 2 and 2 to 3. What is the acceleration? So that's supposed to say when. Another typo there. When is the acceleration undefined on that interval? So the acceleration is undefined. We go back to the graph. So this is where derivatives are undefined. And it's at any change here. Let me get rid of these drawings. So like these changes in functions. So like we have a constant piece, we have a linear, and then we have a linear with a different slope, and then we completely change here. Got like a little corner here. So we have acceleration undefined at these 3 points. So 1, 2, and 3. State an interval of time when the particle has a positive acceleration but is slowing down. So that's going to be from 3 to 5, right? Because they're having opposite signs. The velocity is positive because the slope is positive. The velocity itself is negative, but the acceleration or that slope is positive. So it's got those opposite signs there. So let's look at an interval where the acceleration is negative. So that means the velocity is a slope that's negative. And the particle is speeding up. So they have to have the same sign. So that's going to be from 2 to 3. What is the particle's acceleration over the time interval 3 to 4? So that's asking, what's the slope from 3 to 4? So from here to here. So rise over run. So 5 over 1. So the slope is 5. Unit-wise, it'd be feet per second squared. Remember, acceleration is the change in velocity over time. And velocity was already the change in position over time. What is the particle's average acceleration over that 5-second, the entire 5-second interval? So, okie dokie, we have the acceleration average is going to be the velocity at the end minus velocity at the beginning, and then that 5-second time. So let's see, it was 0 at the end, and then it was 5 at the beginning. So it's going to give me -1 feet per second squared. Over what time interval is the particle's velocity decreasing at a rate of 5 feet per second every second? So we want to, where is there a negative slope of 5? So I have 2 options. I have negative slope here, right? I got from here to here. Rise over run, 5 over 1. Okay, probably there. Let's just double check here. Yeah, that's 10 to 1. So yeah, 1 to 2 is when we have a slope of -5. Oh, from 1 to 2. Let's look at a different one. So model rocket is launched vertically upward from ground level with an initial velocity of 114 feet per second. The position of the rocket can be modeled by S of t is -16t squared plus 114t. So find the velocity and speed at t equals 5. So if we know our position is the function given, velocity is the derivative of position. So that's -32t plus 114. And if we want to do it at 5, just plug in 5. I'll grab my calculator and plug that in. So -32 times 5 plus 114 is going to give me -46. Did it give me, yeah, feet per second. Feet per second. But speed is the absolute value of velocity. So speed is 46 feet per second. Is the rocket speeding up or slowing down at t equals 5? And how do we know? So the velocity is -46 feet per second. We'd want to know the acceleration. So the acceleration is actually the derivative of velocity, so -32. So if our velocity is negative and our acceleration is negative, it's the same sign. So speeding up. Because V and A have the same sign. What is the maximum height the rocket will rise? So finding the maximum height. Can do one of 2 things. The original position function is a downward facing quadratic. So we can use our pre-calc knowledge to find the maximum, right? Which would be -b over 2a. And then we can substitute that in. So -b over 2a. Which gives me 3.5625. And then I could plug that in. And get that maximum height. With calculus, though, we can think of it this way. So we have that parabola, right? That maximum is going to be where the slope is 0. So we know the velocity, right? -32t plus 114. We can find when it's 0. So -32t equals -114. Divide the 2, so 114 divided by 32, and that's going to give that 3.5625. And then we would plug that back into the position function. So either way, we're plugging that into the position. So 3.5625 squared times negative 16 plus 114 times 3.5625, which gives me 203.0625 feet. When is the speed, or what is the speed of the rocket when it hits the ground? So, okay, we want to find when it hits the ground. So again, it's a quadratic. Hitting the ground would be the zeros. So let's take the original function and find when it hits the ground. So I can take a GCF of negative 2t out. I'm left with 8t minus 57. If I set these both equal to 0, I get 0 and 57/8. So I want to find the speed. So it's the absolute value of velocity, right? So velocity was that negative 32t plus 114. So I know my time value is 57/8. And let's find what this is. So 57/8 times negative 32 plus 114 is going to give me a negative 114. But remember, speed is the absolute value. So 114 feet per second. Okay. All right, so something else we might want to look at is the effect of changes, right? And maybe we want to look at, like, what if we just change something by 1 unit? So for very small values at age, the approximation of the derivative, we can find that with the difference quotient, right? And we can say that, hey, the derivative of a value is approximately function value of the next one minus function value of the original. So it's an approximation. So in other words, the derivative is approximately equal to the change in the function by a 1 unit change in x. So let's look at an example. So for speeds between 30 miles per hour and 75 miles per hour, the stopping distance after the brakes are applied for a vehicle can be modeled by this function here, 1.1s plus 0.05 s squared feet. So for a vehicle traveling 65 miles per hour, let's find the actual stopping distance at 65 miles per hour and 66 miles per hour. And then what is the stopping distance needed for that increase of 1 mile per hour? So let's find f of 65. So that's 1.1 times 65 plus 0.05 times 65 squared. Let's see what that is. 1.1 times 65 plus 0.05 times 65 squared. That gives me 282.75. And then let's plug in 66. So 1.1 times 66 plus 0.05 times 66 squared. And that's going to give me 290.4. So if we want the actual stopping distance needed for that change in 1 mile per hour, I can subtract these. So it's 290.4 minus 282.75 to give me 7.65 feet. Okay, estimate the change in stopping distance if the speed increased by 1 miles per hour by using the instantaneous rate of change at 65 miles per hour. So we can find the derivative. So that's going to be 1.1 plus 0.1s. And we can plug in 65. So get 1.1 plus 0.1 times 65. Let's see what that gives. 1.1 plus 0.1 times 65, and that gives me 7.6 feet per mile per hour. And look how close those are. So let's compare. So the actual was 7.65 and the estimate was 7.6. So look how close they are. So that's why we can say it's an approximate for that actual increase. All right, and that is all for this section. So if you have any questions, let me know.